Hey guys, and welcome back to another video. In this video, we'll be talking about optimization. Alright, so let's get right into it.
Alright, so like I said in this video, we're going to be covering optimization. Alright, so in my opinion, the best way to learn optimization is just three examples. Alright, so we have three examples for this video, so we'll just work through each one together. And there's like a little blueprint that is going to help you, that I'm going to tell you, that will help you solve pretty much any optimization problem. Alright, so let's begin with this first example. So we have a rectangular page is to contain 30 square inches of text. The margins on each side are 1 inch. Find the dimensions of the page such that the least amount of paper is used. All right. So the first step in these types of optimization problems is to draw a picture. Okay. So this is like the same step that was in the related rates problem, if you remember. Like the first step in pretty much any of these word problems is just to draw a picture of the scenario. So in this case, we have a rectangular page. Okay. And it contains 30 square inches of text with a margin of 1 inch on each side. So let's say we have some text on the paper, like so, okay? And let's go ahead and find the dimensions of the text. So we'll call this length y and this length x, all right? And then we know the dimensions on, or the margins on each side are 1 inch. So that means that this, all these lengths are 1 inch, all right? So like I said, the first step is to draw and label your picture, all right? Good. So now next, step 2 is to um, identify the constraints on your variables. All right, so identify constraints on your variables. So what do I mean by that? Well, in this case, our variables are x and y, right? And because x and y are dimensions, they're lengths, that means that they must be positive. So that's why we know that x must be greater than 0 and y must be greater than 0, right? So now we have established constraints on x and y. So now any solutions that we get later on must satisfy that x is greater than 0 and y is greater than 0. Okay? So now step 3 is building your equations. All right. So in this case, you can have multiple equations. So in this case, we know that the text has an area of 30 square inches. Okay? So that means that x times y is equal to 30 square inches. Right? Because x and y are the dimensions of the text. And then we want to find the dimensions of the page such that the least amount of paper is used. So if we know the area of the text xy is given by 30 inches, then we want to minimize the area of the whole paper. So the area of the whole paper is given by x plus 2 times y plus 2. And that's because each side of the paper, so like this side, for example, right here, has a length of x plus 1 inch margins on each side. So total, that's a length of x plus 2. And then this length right here also similarly has a length of y plus 1 inch margins on each side. So therefore a y plus 2 in total. Okay, so our area is given by x plus 2 times y plus 2. And so this is the function that we want to minimize. All right, so optimization problems are in essence just applied minimization slash maximization problems. All right, good. So now let's move on to step 4, which is, so step 4, which is to write your equations in terms of one variable only, right? So write your equations in one variable. And the reason for this is that when we go to differentiate in step 5, it just makes the whole process a lot easier. Because otherwise we'd have to use implicit differentiation, and that's not fun. So let's go ahead and express our area function a as a function of x, right? So we'll say a of x is equal to x plus 2, so that's already in terms of x, so that's good. So now we really just need to express y in terms of x. Well, we can use this equation right here, x times y equals 30, and solving that for y, we get y is equal to 30 over x, right? So therefore, we can substitute this in for y right here, so we get 30 over x plus 2, all right? And then we can simplify this, so we get a of x is equal to, if we distribute, we get x times 30 over x, so the x is canceled, left with 30, plus 2x, and then distribute this 2, so we get plus 60 over x plus 4. All right, so now this right here is our equation that we're going to want to minimize in this case. All right. So now finally, step 5 is to differentiate and then find your min-max values. Differentiate slash find min-max values. Okay. So let's go ahead and differentiate a of x. So we get a prime of x is equal to 2 minus 60 over x squared, right? Just by the power rule. And let's go ahead and set this equal to 0 to find our critical points, right? So basically, for this case, we're basically going to be using the first derivative test to find our critical points of a, and then seeing if and making sure like it corresponds to a relative minimum, a local minimum in this case. Technically, you could use the second derivative test, but for most of these problems, using the first derivative test is the preferred method, right? It's just easier. But anyway, so we have 2 minus 60 over x squared equals 0. So we can move the 60 over x squared to the other side. So we get 2 equals 60 over x squared. So 2x squared equals 60, and x squared equals 30. Okay, so now let's go ahead and take the square root of both sides. So we get x is equal to plus minus square root of 30. But now this is when our constraints come in useful, because we know that x is greater than 0. So therefore, we only want the positive square root. All right, so let's go ahead and we only want the positive version. All right, good. So now the only thing left to check is to make sure that at x equals square root of 30, our area function a of x actually does have a local minimum. All right, so like I said, we're using the first derivative test. So let's go ahead and build our number line now. So this is for a prime. So we have square root of 30 right here. And let's go ahead and test values of a less than square root of 30 and greater than square root of 30. All right. So if you test values of x less than square root of 30, you get that the derivative is negative. And for values greater than square root of 30, you get that it's positive. So therefore, by the first derivative test, a does have a local min at square root of 30. All right. So this is correct. But now let's go back and see what the question is asking us. They're asking us to find the dimensions of the page, right? Find the dimensions of the page. So we know the dimensions of the page, as given by this formula right here, is x plus 2 by y plus 2, right? So that means that the dimensions of the page, so we know that x is equal to square root of 30. So let's go ahead and solve for y from this. So we know that x times y must equal 30. So square root of 30 times y is equal to 30, so therefore y is equal to square root of 30. And again, square root, y must be positive, so it's the positive square root of 30. But now that we have x and y, we can go ahead and find the dimensions of our page. So it is square root of 30 plus 2 by square root of 30 plus 2. All right, and this is approximately 7.477 by 7.477 inches in this case, right? Good. So let's go ahead and review real quickly. So our first step in these problems is to draw and label a picture, all right? And so we did that. We drew our piece of paper and we labeled our variables and what we knew, all right? So then the second step right here was to identify the constraints on our variables. So that basically just means to give like intervals for our variables based on the context of the problem. So usually it's going to be that the variables have to be positive and they can't be negative. All right. And then step 3 was to build an equation. So we went ahead and we built two equations from what we knew. We knew that x times y was equal to 30. And then we constructed an area function, x plus 2 times y plus 2, right? And then in order to differentiate that area function more easily, our step 4 was to write our equations in one variable. So we went ahead and we expressed everything in terms of x. And then finally, step 5, we differentiated our area function, found its critical points, and then solved the problem right here. All right, good. So now let's go ahead and do another example with this exact same setup. All right, so we have two factories are located at the coordinates x0 and negative x0, and their power supply is at 0h, as shown in this figure right here. All right, so now we want to find y such that the total length of power line from the power supply to the factories is minimized. All right, so we already have a picture, right? So step 1 for us is complete. All right, so that's good. So now step 2 is to identify the constraints on our variables. Well, first let's notice that h and x are actually not variables. Okay, they're not variables, they're constants. And that's because the problem gives them to us, right? They tell us that the two factors are located specifically at x0 and negative x0, and that the power supply is specifically at 0, h. So h and x are not variables. Therefore, the only variable we have in this problem is y. All right, so then the constraint on y, notice that y is like right here in between h and 0, right? So therefore, the constraint on y is that it must be between 0 and h. All right, good. So now we have built a picture, or rather it was already built for us, and then we have identified the constraints on our variable so that it makes sense in the context of this problem. So now step 3 is to build an equation. Well, what do we need an equation for? We need an equation for the total length of power line. All right. So the power line is basically like this bolded lines right here on my picture. So we want to find the total length of all three of those line segments. So this first line segment right here, that's pretty easy. The length of that is just simply h minus y, right? So I'll call our length function L. So we have that h minus y length for that first vertical strip. All right, good. And so then now let's find the length of both of these segments. And let's begin by noting that both of these segments have equal length. So if we can find the length of one of them, we automatically know the length of the other, right? And so to find the length of this diagonal strip line segment, we can construct a right triangle with base length of x and height of y, right, as given in the problem. So then we can just use Pythagorean theorem to find the length of the hypotenuse of this triangle. So we have x squared plus y squared equals, I'll call this length c, so c squared. And so therefore c is equal to the square root of x squared plus y squared. And like I said, this is also the length of this other line segment over here. So therefore, in total, both of these line segments combined have a length of 2 square root of x squared plus y squared. All right. So therefore, our total length function L is h minus y plus 2 square root of x squared plus y squared. All right, good. And this is a function of y, because remember, y is our only variable in this case. So then step 4 is automatically taken care of. We don't have any variables except for y, so that's already good. We already have L in terms of one variable. So now we can move on to step 5, which is differentiate. All right, so let's go ahead and differentiate L of y with respect to y. So derivative of h with respect to y is 0 because it's a constant. And then derivative of negative y with respect to y is negative 1. Plus, we have 2 square root of x squared plus y squared. All right, so let's go ahead and differentiate that. So we have 2, I'm going to rewrite it as 2 times x squared plus y squared to the 1/2 power, right? So then by the power rule, the derivative of this, so derivative with respect to y of this is equal to, we have 2 times 1/2 x squared plus y squared to the negative 1/2, and then times the derivative of the inside, because remember we have to use chain rule, and so that's times 2y. Because x squared is a constant, right? So the derivative of a constant is just 0. So we could just treat this whole thing as just like some constant. So it's just derivative is 0. And so we just have this y squared right here. And so differentiating that, you get 2y. Okay, good. And so then notice that now the 2 and the 1/2 cancel. So we're left with 2y over the square root of x squared plus y squared. All right, so we can put that right over here. So I'm going to just delete this real quickly and just instead move it over right here. All right, good. So we differentiated our function. So now let's go ahead, set it equal to 0, so then we can find our critical points. So we get that 2y over square root x squared plus y squared equals 1, right? So then that means that 2y equals square root of x squared plus y squared. We square both sides, so we get 4y squared is equal to x squared plus y squared. So then we get 3y squared equals x squared, and y squared equals x squared over 3. So now before we take the square root, let's go ahead and come back up here and investigate our constraint, right? So here we have that y must be greater than or equal to 0. So therefore, we want to take the positive square root in this case. So we take the positive square root of both sides, all right? Then we get y is equal to square root of x squared is just x, so we have x over root 3. So this is one of those interesting cases where our variable y that we're solving for actually depends on x, because technically x is a constant in this case, right? So technically y is a constant, but we don't know what x is, so therefore we have y in terms of x. All right, but this is the answer. Y should be whatever x is divided by square root of 3. All right, very good. All right, let's move on to our next example. So in this example, we have a lifeguard is standing on the beach 1 meter from the shoreline. A swimmer is in the ocean 2 meters from the shoreline. The horizontal distance between the lifeguard and the swimmer is 3 meters. The lifeguard can run at 4 meters per second and can swim at 2 meters per second. At which point on the shoreline should the lifeguard transition from running to swimming to reach the swimmer in the least possible time? Okay, so like always, our first step is to draw a picture. So I'm going to go ahead and draw our picture on the coordinate axes, because as we will see, that will make this problem much easier to solve. All right, so let's go ahead and put the swimmer right over here. And let's say our x-axis is the shoreline. So then our swimmer is 2 meters from the shoreline. So this coordinate point is 0, 2. Okay? And then our lifeguard is 1 meter from the shoreline and then 3 meters from the swimmer. All right. So therefore, the lifeguard is at the point 3, negative 1. All right, so this is our swimmer, and this is our lifeguard. All right, very good. So now that we have a picture, our next step is to identify constraints on the variables. Well, let's see what our variable even is in this case. We want to know at which point on the shoreline should the lifeguard transition from running to swimming so that she can reach the swimmer in the least possible time. So that means that there's some point on this shoreline on the x-axis. So that means it has coordinates x0, such that the lifeguard transitions from going onto the beach into the water. So in this case, our variable is x. And so we know that x can be, x must be positive. Okay, so x is greater than or equal to 0. And it also must be less than or equal to 3, since the total distance, horizontal distance between the swimmer and the lifeguard is 3, right? So like the lifeguard's not going to go backwards. That's obviously going to be inefficient. All right, so this is our constraint on x. All right, good. So now let's go ahead and build an equation. Well, so we want to minimize time, right? So we want a function of time. We want like some function t of x. All right, so this represents the total time. So we can break this up into the time the lifeguard takes on the beach plus the time the lifeguard takes on the ocean, right? So on the beach, how long does the lifeguard take? Well, we have to use a special formula. Its distance is equal to rate times time. right? So in other words, we have time is equal to the distance over the rate. So we already know the rates of the lifeguard, right? The lifeguard can run at 4 meters per second on the beach and swim at 2 meters per second in the ocean. So the rate variable r is taken care of. So the only thing that we have to find is the distance. And so we want to find this distance right here, and then we want to find this distance right here. Okay, so let's begin with that first distance. So we can go ahead and draw a sort of right triangle, and I'll make that triangle bigger for you guys over here. So if we replicate that triangle, this point right here is 3 minus 1, and this point right here is x0, okay? And we want to find this distance right here. So I'll call it the beach, the distance on the beach, okay? So this is a right triangle, so therefore we can just use Pythagorean theorem. Well, how long is this length right here? Well, if this length, so we know that this length right here is x, right? And the total length is 3. So therefore this length right here must be 3 minus x. Alright, so this length right here is 3 minus x. And then this vertical distance is just 1. Alright, so therefore by the Pythagorean theorem, we have that the distance on the beach is equal to the square root of 3 minus x squared, 3 minus x squared plus 1 squared. Alright, good. So now let's do a similar thing for the distance on the ocean, distance in the ocean. So we have this right triangle now, okay? So again, I'll make that triangle bigger for you guys over here. So we have this point up here is where the swimmer is at, 0, 2, and then this is again x0. So and this is our distance in the ocean. All right, so this vertical length right here is 2, and this horizontal length right here is x. So therefore, the ocean is equal to the square root of 2 squared plus x squared. All right, good. So now let's find our time on the beach and our time in the ocean. So come over here. So our time on the beach, by this formula right here, it's equal to the distance on the beach over the rate on the beach. So the distance on the beach we have already determined by this formula over here is given by the square root of 3 minus x squared plus 1 squared, which is just 1, all over the distance on the beach. So the distance on the beach, or sorry, on the rate on the beach. So the lifeguard can run at 4 meters per second on the beach. So that's the rate. All right. So just simply 4. All right. Very good. So now let's find the distance or the time it takes the lifeguard in the ocean. So that's equal to the distance on the ocean. So that's the square root of 2 squared plus x squared. So I'll just write that as x squared plus 4 square root, all over the rate on the ocean, which is 2 meters per second. Okay, so divided by 2. So then now our total time function, t of x, is equal to our time on the beach plus our time on the ocean. So it's equal to the square root of, and 3 minus x squared, x minus 3 squared are the same thing. So I'm just going to write this as x minus 3 squared plus 1 all over 4, and then plus our time in the ocean, which is x squared plus 4 square root all over 2. All right, very good. So now let's go on and move to step 4. So step 4 is just saying that we have to write our equation in one variable, but that's already done for us. It's already in terms of x only. So then let's move on to step 5, which is differentiate. All right, so we have our function t of x as given here. So we can go ahead and rewrite this as 1/4 times x minus 3 squared plus 1 to the 1/2 power. But I'm going to go ahead and expand that out. So x minus 3 squared, that is x squared minus 6x plus 9 plus 1. And so that just it becomes plus 10. All right, all to the 1/2 power. And then we have this, it can be rewritten as 1/2 times x squared plus 4 to the 1/2 power. All right, so now let's go ahead and differentiate. So we have t prime of x is equal to 1/4 times 1/2 x squared minus 6x plus 10 to the negative 1/2 power. So that's by the power rule. And then now we have to multiply by the derivative of the inside because of the chain rule. And so that's we multiply by 2x minus 6. And then plus we have 1/2 times. So the derivative of x squared plus 4 to the 1/2, that is 1/2 times x squared plus 4 to the negative 1/2, and then again multiply by the derivative of the inside, which is 2x. Alright, so then in total we have t prime of x is equal to, let's see, so we have 2x minus 6 times that 1/2 out front, so that just becomes x minus 3. So we have x minus 3 all over 4 times the square root of x squared minus 6x plus 10. And then we have, again, this 1/2 times this 2x, so that just simplifies down to x. So then we have x over 2 square root x squared plus 4. All right, so now we can set this equal to 0 to find our critical points. So I'm going to move this fraction over to the other side. So then we have x minus 3 all over 4 root x squared minus 6x plus 10. That's equal to negative x over 2 square root x squared plus 4. All right, so now we can go ahead and square both sides. So we have x minus 3 squared, so that's just x squared minus 6x plus 9 all over this denominator squared. So 4 squared is 16, and then the square root and square cancel. So we're just left with x squared minus 6x plus 10. And that's equal to negative x squared is simply just x squared. And then again, in the denominator, we have 2 squared, which is 4. And then the square root and square cancel again. So we have x squared plus 4. All right, very good. So now we can cross multiply. And so then on the left-hand side, we get 4x squared minus 24x cubed plus 36x squared plus 16x squared minus 96x plus 144, and that's equal to, on the right hand side, we have 16x to the fourth minus 96x cubed plus 160x squared. All right, so now let's move everything to the left hand side and set this thing equal to 0. So we have negative, or sorry, this is supposed to be a 4. Okay, so we have 4x to the fourth. So then we have negative 12x to the fourth plus 72x cubed minus 108x squared minus 96x plus 144, and that's equal to 0. Okay, and so then notice that very conveniently we can divide both sides evenly by negative 12. And so that's very nice because now the left-hand side simplifies to x to the fourth minus 6x cubed plus 9x squared plus 8x minus 12 equals 0. Okay, good. So now to solve this quartic equation, we have to use the rational root theorem. So if you don't know what the rational root theorem is, I have covered it in my pre-calculus series, so I definitely recommend you go ahead and check that out. But basically what you do is you find your constant term. So in this case, we have negative 12. And then you find all the factors of negative 12. So it's plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, and plus minus 12. All right. And then you find your leading coefficient. And in this case, that's just a 1. And so then the factors of 1 is just 1. All right. And so now you have to find the fraction a0 over an. And so because an is just 1, this is simply just equal to a0. So we could just rewrite all our factors for negative 12 here. Okay, good. So now what we have to do is, using synthetic division, we have to test each of these roots essentially and see if they give us a remainder of 0. So just to save us from like the tediousness of that, I have done this beforehand, and I'll just tell you guys that if you try 1, positive 1, the synthetic division works out, and so that means that x minus 1 is a factor. Alright, so then this polynomial right here, this quartic, becomes x minus 1 times the quantity x cubed minus 5x squared plus 4x plus 12, and that whole thing is equal to 0. So then from the x minus 1 equals 0, we get a solution of x equals 1. And actually, this cubic polynomial only gives us a negative root. And so if we go back to the constraints of this problem, way back up here, we mentioned that x must be between 0 and 3. And so therefore, a negative root in the context of this problem is extraneous. So we don't care about this root. So therefore, our only solution to this problem, our only critical point, is x equals 1. And so that means that the time is minimized when this when the lifeguard goes through this point when x is equal to 1. So at the point 1, 0. All right, very good.
Alright, well, that wraps up this video on optimization. If you found this video helpful, please make sure to leave a like and don't forget to subscribe. I'll see you guys in the next video.